A semicircle plate of radius 5, fully submerged 2 feet below the water surface. Find the hydrostatic force. Since the unit is in feet, the force, we know that it is rho GAD, but this is only in the metric system. In the customary system, the rho g is the density. So we only need the density times the area times the depth in this case. In this video, we will show different setups. Hopefully we'll get the same answer. In this case, if we set 0 so that it is at the water level, then the center of the circle is x equals 0 and y equals 7 with the positive y-axis pointing downward. The top of this circle is therefore 2, that is 2 feet below the water surface. The radius is 5, and that is why when we get to the center, 0 to 2 is 2 units, another 5 unit is 7. To find the force, we would need to slice this plate horizontally. Everywhere on this slice has the same distance from the water level. If we position the coordinates so that the positive y-axis is pointing down, then the distance from the origin y equals 0 to where we slice is y sub I. The area of the slice is the width times the delta y, the delta y being the thickness of the slice. If we were to find the width, we use the right triangle as shown in the figure. With this right triangle, the hypotenuse is the radius of the circle, which is 5. The width is twice the horizontal side. In this case, we would label this x sub I for now. The vertical leg has a length of 7 minus y sub I, because from the origin y equals 0 to the slice, that is y sub I already. When we get to the center of the circle, y equals 7. So to find the vertical length, we would take the larger y value, which is y equals 7, minus the smaller, which is y sub I. Depending on where we slice it, we would have a different value for y sub I. From this right triangle, we see that x sub I squared plus 7 minus y sub I squared equals 5 squared using the Pythagorean theorem. X sub I squared is therefore 25 minus 7 minus y sub I squared. And so x equals the square root of 25 minus 7 minus y sub I squared. The width is twice this distance. And so the area is the width, which is 2x, but x is the square root of 25 minus 7 minus y sub I squared times the thickness, which is delta y. And so in this formula, we have the density, which is 62.5 pound per cubic feet. The area is 2 times the square root of 25 minus 7 minus y sub I, the quantity squared times delta y. We still need the depth. The depth from the water surface to the slice. We position the coordinates so that y equals 0 is where the water level is. And so from the slice to the water level, it is a distance of yi. So the depth d is y sub I. The force at the slice is therefore density 62.4 times the area 2 times the square root of 25 minus 7 minus y sub I squared, and then the depth is y sub I and the delta y is part of the area. The total force turns to the Riemann sum as I go from 1 to n. Density 2, the square root of 25 minus 7 minus y sub I squared, yi times delta y. For the integral, we would integrate this. 2 is a constant factor, so we can put it in the front of the integral, so is delta. The square root of 25 minus 7 minus y squared, y outside of the radical, and then dy. We only add up the slices where the plate is, which is from 2 to 7. The lower limit of integration is 2 and the upper limit of integration is 7. We only integrate where we can slice the plate. It is now okay to put this integral into a calculator and obtain the answer 11,972.25 pounds, which is the units of force. It doesn't matter how we position the coordinate system. Let's set it up a different way to see if we get the same answer. Suppose this time we put the origin at the center of the circle with the x and the y axis as usual, the positive y pointing up. The radius of the circle is 5, so this is y equals 5, and the water level is 2 feet above the top of the semicircle. And so the water level is at y equals 7. We then slice this as we would normally do. The thickness of the slice is delta y. Using the right triangle still. With this right triangle, the hypotenuse is still 5, which is the radius of the circle. We label the horizontal legs x sub I. This time though, where we slice it is y sub I, and so the vertical legs is no longer 7 minus y sub I, but it is y sub I. It is the distance from the origin to the slice. With the vertical leg be y sub I, x sub I is simply 5 squared minus y sub I squared, the square root as it should be, because we put the circle at the center or at the origin, and so the equation of the circle is x squared plus y squared equals 5 squared, which is what this is saying. And so the width of the slice is twice this distance x. The area this time is 2 the square root of 25 minus yi squared. This is the area of the slice times the thickness delta y. And so the force at the slice this time is the density times the area, which is 2 square root of 25 minus y sub I squared delta y. We still need to find the depth. The depth is always from the water level to where we slice. We take the upper y, which is 7, minus where we slice, which is y sub I. And so the depth is 7 minus y sub I. We put this in the Riemann sum and obtain the integral to delta. Delta is the density 62.5. The square root of 25 minus y squared, and the depth this time is 7 minus y. Delta y turns to dy. This time, we add up all of the slices from y equals 0 to y equals 5. And so the lower limit of integration is 0, and the upper limit of integration is 5. Put this in the calculator, we will get 11,972.25 pounds, which is the same answer we got before.